Hi, my name is Devin and I'm here today to walk you through a workflow for segmenting soil and plant X-ray CT images with deep learning and Google's Colaboratory. You can find the code here on my GitHub at github.com/rip/XCT_FCN. And you can find all the relevant code, instruction here on GitHub, a connection to some instructional videos that will be posted on YouTube. You can access a preprint of the publication at Archive. And then you can also access the testing and training data here at the National Ag Library. And so to get started, I'm actually going to open up the code first. And then I'm also going to open up the connection to the National Ag Library. So I'm going to start the download of the data set that we're going to be training on today. And so we're going to use this annotated X-ray CT images and mass walnut leaves. So we're going to go ahead and start that download, and then we'll unzip it soon. While we're doing that, we're going to take a look here. So here's the code for the workflow, and we can actually open it up in a Colab notebook like this. And I'm just going to switch my accounts right now. So that's just opened up. And so we can run this block. And you're going to get a warning because this was authored by me, not Google. And so just hit run anyway if you trust it. There's nothing malicious about it. So now we're going to connect to Google Drive. And so this is going to read and write from your Google Drive account, and so that's what it's doing here. It's connecting to my Google Drive account, and so this is where all the files and folders will read and write from and to. So let's take a look. So right now it's connecting, and then the next thing we're going to do is check out our GPU allocation. So we can just close that. It has connected. Great. Oh, wow. So we are on A100 today. That's nice. That's because I have Google Colab Pro Plus. So this should make training and validation very speedy today, which is great. This code will work just fine on GPUs with less VRAM. Earlier I was on a V100. I'm often on P100s or T4s. All those have about 16 gigabytes of VRAM, so this should run just fine. Small image sets will run just fine, say 500 by 2000 pixel images will run just fine without downscaling on video cards with 16 gigabytes of VRAM. With this A100, if you are able to get access to it, you can run about a 2000 by 2000 pixel image without downscaling, which is pretty nice. Okay, so here we go. So here we have our input directory. So basically we want to make sure that we input all of the materials that we want to see in our images, and this is based on our training image data. And so we are going to have training images and masks. The masks will be labeled with grayscale values and of the specific things that we want to see. And so in this case with these leaves, the masks, which we can see, well, let me unzip this and we'll move forward from there. I'm going to upload the images and masks that we'll be training from to my Google Drive. So let's get started with that. Okay, almost done extracting the images. Perfect. I'm now done with that. So I'm going to make a new folder here in Google Drive for this, and I'm going to call it a workflow test. Great. And so I'm just going to create that folder. Let's see what happens. Great. Came up right on top. And so now I'm going to upload all the masks and images to this. And so let's do that right now. So we're going to have 4 folders in total that we're adding here. I'm going to make a 5th folder called Best Models. You're going to want to make this folder when you want to train your models. And so These two folders are images and masks for training, and then these two folders are images and masks for testing. So the images that are in our testing folders are not used at all during training, and in fact are taken from a leaf and a tree that the model will not train on. So let's see how a generalized model based on 5 sets of training image data does when it's evaluating a leaf that it has never seen before. So we have this all set up for Google Drive to read and write from. And so in order to make sure that we're connecting to the right folders, we can go over here and click on the folder icon. We can then click on My Drive, and this should populate here. And let's see. Okay, so here's our workflow right here. So we're going to go ahead and say, here's our training images. So we're actually just going to copy this path right here. And if we copy it and paste it directly, you'll notice that there is no / at the end. Please put a / at the end. It's necessary to read inside of this folder. And so we're going to just kind of repeat this. So here we're going to copy the path for the masks, right? So we've done that. And now we're going to copy the path for the best models. And again, we really want to make sure that that / is included at the end so that it will read and write into these folders. Here's our model group. We're going to modify this. So we're actually going to change the number of models that we're going to make here to 1 and our number of epochs to 30. This will just speed it up for demonstration purposes. I kind of like to save these parameters in the model group name and the model and in the model name. And so we'll do that here. Great. So now for testing, we're also going to want to make sure that we're linked to the right read and write folders. So that's what we're doing now. So let's copy this path right here over, and we're going to take some of this data right here, and we're going to adjust that. So we want to make sure that the CSV directory that it's going to write a CSV to is correct, and so we're going to have it write to a workflow test folder, and we're going to change the name. So we're going to say it's going to be it's basically one model of the leaf data, and we'll say it's 30 epoch, and yeah. So great, so we've modified all that. Now for inference, we're actually going to have it evaluate these test images that it's never seen. It'll be good for us to see how it does. Numbers are great. Getting a recall and precision value is great, but I really like to see the actual outputs to see if it's doing what I want it to do. For inference, you're going to want to make sure that you tell it what is preceding the numeric character of your image and what is following the numeric character of your image. So in this case, it would be something like mage and tiff, but that's in this case. For these images that we're working with right now that we'll be evaluating, the name is 411_R3_sep_slice. So we're going to have this LICE_ as the preceding part, and then the .png as the following part. And so it's going to then read each of these in order from 1 through 5 and evaluate them. Okay, so now that we've done that, the only thing left to do is to change our output directory. So we're going to change our output directory to read into that folder that we've set up in our drive, right? And so we're going to say, we're going to call this a test output, right? And so we're going to have that / here at the end so that it will write into this folder. And so with that, we'll let it go. So now we're going to do parameter loading. So this is a batch normalization step. And so we're basically getting it to make sure that it uses something called albumentations during training to help reduce any overfitting. And then it's also going to do batch normalization. For any model that you generate, you're going to want to make sure that you have the correct image directory loaded, because it's always going to batch normalize off this training image directory. So if you train a model, You're going to want to make sure that you save those images that you trained off of and keep them in your training image directory and training mask directory locations so that it can do the correct batch normalization. So it's done the batch normalization. Previously, the mean value in the images was 0.4932 with a standard deviation of 0.550. It has now made through batch normalization, it's now set the mean to about 0, and the standard deviation to 1. So this is normal for FCNs. And so now we're going to start training our model. In order to train the model, we're just going to run this code. And there we go. It should be off to the races right now. So it's starting to train. We're on an A100. This is a very fast video card, so training is going to get done very quickly. It is going to be 30 epochs. So, this is probably going to take about 4 or 5 minutes. Feel free to fast forward through this part while it's just training up the model, and I will catch up with you when model training's done. Great, the model training is finished at this point. And so it's gone through 30 epochs. Python numbering starts at 0, so 30 epochs would be from 0 to 29. And so let's see kind of how it did. We'll do validation right now, so we're going to just run this validation code block. It's going to download the model and see how how we did. Okay, so the results are pretty good for only training for 30 epochs. We can see that our F1 scores are generally above 75%, except for the vein, where the F1 score is about 60%. Still, this is represents about as good as any other method for generating models can do, and is faster and more flexible than pretty much anything else. Okay, so we are going to save this output as a CV, and so it's going to actually right here, and so it should just pop up in a second. There it is. So we can open that up and we can, get these scores. If we train more models, it would just, you would have another set of model number 2 that would have the same precision, recall, accuracy, and F1 scores for your data. And again, this validation is, or this output is based on testing done on a completely independent set of images that the model has never seen before. That's extremely crucial. You want to make sure that your model is accurate, even on data that it has never seen. And so you have to make sure that you're testing it on data that it has never seen. So we got these results. So now we're going to load up our model right here. So model number 1, because we only trained one model, we're going to let it load up. Okay, so it's loaded up. And now we're going to segment that test data and take a look at it and see what it looks like. Okay, so it is currently segmenting the data. It is done. It only had to segment 5 images, so that's not a lot. It's saved here to this test output folder. We can open that up, and it's in the process of saving everything there. So let's take a look. Okay, so here we go. We have what looks approximately like a walnut leaf. So it did a fairly good job. Here we have the background. The epidermis is right here. Bundle sheath extension, and then the veins. Some areas where there's overlapping predictions, you kind of you'll get this color change. And so one way around this overlapping prediction problem is just to tighten up the recall and precision. So you can always kind of tighten up how the model is actually making predictions by changing these values here. As you go down in value closer to 0, it will make predictions on data, or it will make predictions that it's less sure of, and as it gets closer to 1, it will make predictions that it's more sure of. And so if we want less overlap, a lot of times we can just increase these numbers and we'll get less overlap. So it did a reasonable job. If we want to see kind of what the original training mask looks like, here's what the original training mask would look like. So we got something that looks approximately like this. So not bad for about 5 minutes of training. Yeah, and so we can kind of go through, say, a stack of 500 of these and get do inference on them, segment them in 10 to 15 minutes, which is pretty quick. One of the other great parts about this is you will get, say, binaries of everything. So this is a binary, the airspaces. So you can always stack these up and run like open horn network models on them to look at connectivity, things like that. So it's nice to get these binaries. You also will get a CSV out of this that has each of your material classes that you specified and the area and perimeter of them in each image. And you have that for each image, so you can sum up these areas. Say here's the epidermis area, and you can get a volume in, so you can understand the volume of, say, the epidermis in any images that you're looking at. Okay, so with all this in mind, I am going to show some areas now that people can get tripped up on. So one area that people can get tripped up on is, certainly not having these forward slashes in the right places. Make sure you have those in the right places. Some other areas that people can get tripped up on are if the file names are not the same for training, it will cause problems. So right now I'm going to change this first name from slice 1 to slice 11. Currently there's a mask called slice 1, but there will be no masks called slice 11. So I'm just going to change that right now, and we'll come here, we'll have it reconnect to my drive so it can update what it thinks the right folders are. I'll tell it what folders it should be reading and writing from, and we'll get it to load the parameters right now. And it's going to throw an error. So it says either no mask or multiple masks found for the ID copy of 53_R3_ slice 11. And that's because there is no mask called with that name, right? So we can look at the masks here, and we do have a slice 1, but we don't have a slice 11, right? So that's why it's throwing that error. So if we rename this slice to, say, 11, and we rerun this, it should run just fine, right? So we're going to go through and look at our materials, boom, and then we'll load our parameters right here. Let's see how it does. And we see no problems. Does the batch normalization just fine. So another issue can be if you modify the batch size, or if your images and masks are not the same size. So your images and masks must have the same number of pixels in them. So the X and Y dimensions of your images and corresponding masks must be the same size. If they are not, it will throw an error. Now, if you change your batch size, say you increase the batch size to 2, you need all of your images then that you're training on to be the same size. With a batch size of 1, you can have variably sized images and it can train just fine. But as soon as you have a batch size of 2, your images must all be the same size. And that's because it will load up 2 images at a time for learning when you have a batch size of 2. If you have a batch size of 1, it will only load up 1 set of images at a time for learning. And so it does not matter what their sizes are. With a batch size of 2, it does matter. So we're going to go ahead and show that. So we have a batch size of 2. Now we're going to try to do the parameter loading. It's going to load up 2 images at the same time, and it's going to say, oh, well, these images are not the same size because one of them, both have a bit depth of 3 here, but the Y and X dimensions of this image are 405 and 1422, while for this image they are 417 and 1443. So these are different sized images, and it cannot train on those. There are ways to get around this. You can crop all your images to the same size. You can actually add pixels to your image to make them all the same size. We haven't done any of that here, mainly because when training on small data sets, it's usually okay to have a batch size of 1. You know, we're not training on a COCO data set here, right? We're not looking at 1 million annotated images. The goal is to be able to annotate something like 10 to 50 images and be able to train a nice model off of that, and that's what we can do. And so we can have a batch size of 1 and everything will work just fine. So here, we've changed our batch size to 1. Oh, I didn't rerun that code block. Okay, so let me double check. Batch size is 1. Great, we're going to go to our parameter loading right here. And there, it loaded just fine. Yeah, so hopefully that will help you troubleshoot any issues that you might have. Please feel free to reach out to me to my email, devin.ripner@usda.gov, or on Twitter @dripner. Either of those are good places to reach me. Thank you for your time. I hope this model helps you with your science, or I hope this workflow helps you with your science, and I look forward to seeing what people do with it.